Okay, everybody. We're going to continue on today in chapter 13. I figure it will take at least today's lecture and Thursday's lecture to get us through chapter 13. For some reason, chapter 13 always just seems to drag on, but we'll get there. Chapters this semester seem a bit longer than they were last semester, and we have fewer chapters, so that's kind of the effect that we're getting into. Now, let me kind of remind you where we were last time. We were talking about saturated, unsaturated, and supersaturated. So just to kind of get us back on track, saturated means the solution has exactly the maximum amount of solute. Uh-oh. Is there something wrong? Okay, bye-bye. Okay. Nothing's wrong. Alright, saturated, unsaturated, supersaturated. Saturated means the solvent is holding the exact amount of solute that it can hold. That's the maximum. Okay? If more solute were added and that solute were a solid, it would just settle to the bottom of the container and sit there. And then what we would see at that point is what's referred to as a dynamic equilibrium. So if that was my liquid, okay, and here. Ooh, I can even do it this way, look. New toy. So, if this was our liquid, okay, and we had excess solid in here. So there's some of my solid particles floating that have dissolved up. The extra solid would sit down here at the bottom, and if a piece jumped up, then one of these would come back and get stuck. Okay? So, something jumped up here, something would have to come back here. Alright? And that's what we mean by dynamic. The number of particles up here in the liquid phase would remain constant, but the exact particles that were in the liquid phase would continuously change. And we can monitor this by actually using radioactive particles. And when we do that, we can watch them move from the solid into the solution phase and back out. Okay? Now, if something is super saturated, well, let's go to unsaturated first. If we have something that is unsaturated, an unsaturated solution has more room for more solute. So if I were to dump some more solid, let's say, in, and sugar was my solute, and it was unsaturated, if I dumped more sugar in and I stirred, the sugar would dissolve up until we reach the saturation point. If something is supersaturated, you're actually holding more solvent, the solute, than is possible for that solute to hold. You've tricked it in a way. If we're talking about water and table sugar, if you increase the temperature, you actually increase the solubility of the table sugar. And so if you make a saturated solution at a high temperature and you slowly bring down the temperature, that solute will stay into solution until maybe you bump the container, where a piece of dust falls into the container, or a sugar crystal falls in, and then solid sugar comes crashing out until the solution becomes only saturated again and not supersaturated. So that's the difference between saturated, unsaturated, and supersaturated. No. I want this. Go up. I want to close this. Okay, now I go up. Yay! Now, I've mentioned the word miscible before, but just let me remind you, miscible is when the two components or the components of a solution will mix in any ratio. Okay? Alcohol and water, ethyl alcohol and water are miscible. They'll mix in any ratio. So we don't talk about the solubility of something that's miscible because they'll mix in any ratio. And whichever one's present in the larger amount becomes the solvent, and the one that's present in the smaller amount is usually considered the solute. Okay? When we're talking about a saturated solution, we're talking about its solubility. No, that's not what I told you to do. Okay? Solubility is the concentration of solute in a saturated solution. Now, there's lots of different ways to express solubility. Okay? Now, concentration is the amount of solute per given amount of solvent or solution. Okay? The most common way that we express concentration is molarity. Now, we calculated molarity last semester. This is kind of a review. Remember that molarity, capital M with a nice straight legs, is moles of solute over volume of solution in terms of liters. Okay, just some handy reminders. Remember that to get moles of A, I can take mass of A divided by molar mass of A, or you can think of it as moles of A is equal mass of A, and the molar mass would be 1 mole of whatever over its gram amount. So let's do a couple of problems here, where we're going to look at calculating a molarity, just to make sure that we're all kind of in the same spot. So let's look at problem 48 on page 577 in the textbook. So 577. Okay, now if we look at the problem here, okay, problem 48. Let's see. Then what we see is an aqueous potassium nitrate solution is made by using 72.5 grams of potassium nitrate diluted to a total solution volume of 2 liters. Calculate the molarity, mass percent of the solution. We're not going to worry about anything but molarity right now. We'll come back and do molality in a minute. But for right now, all we're going to do is look at molarity. Okay? So, got my handy dandy calculator, and I'm going to grab a periodic table, and let's play. Well, actually, we can switch over. Yay! Now, let's go whiteboard. Come on, whiteboard. Let me erase here. All right. Now, let's write down the pieces of information that we've got. Okay? If I look at problem 48, we've got .5 grams of potassium nitrate, and we've got a volume of 2.00 liters. And we want to find molarity. Okay? Now, if I look at this, we know that molarity is going to equal moles of solute over volume of solution in liters. So my first step is to take my grams of potassium nitrate to moles of potassium nitrate. So I'm going to go grams of potassium nitrate to moles of potassium nitrate. The tool we need to do that is molar mass. So 1 potassium, that's 39.098, plus 1 nitrogen, 14.007, plus 3 oxygens, 3 times 15.9994. So 1 mole of KNO3 has a mass of 101.1032 grams. Alright, so our step 1 is to go from grams to moles. So 72.5 grams potassium nitrate, 1 mole of potassium nitrate for every, that should be 101, I don't know where that one went, 101.1032 grams of potassium nitrate. So do the math. And I get 0.71708 moles. Now guys, that's overkill on significant figures. Remember, we don't worry about significant figures until the very end of the problem. So to calculate the molarity, it's going to be the 0.71708 moles divided by 2.00 liters. I get 0.3, and thinking about significant figures, this had 3 sig figs, this had 3, so it's going to be 0.359 moles per liter. Or you could just write the big M. Everybody see where everything came from? Just kind of a reminder of what we did last semester. Okay. Alright, now, get back to the screen. Now, we should be able to do that without any problem. And if we were given molarity, we ought to be able to go back the other direction, let's say, and calculate how many grams of something we would need to, make a certain volume of solution. So let's try kind of a go back the other direction problem. Erase. Normally, guys, I will be going to the board, but I'm trying to record this, and what I do up here on the screen get shot onto the computer, and I have a GoPro set up on the computer. And so normally I'll spread out and just kind of work my way around the room. I just got to get chapter 13 recorded. All right, so let's say I ask you something like, how many grams of NaCl do we need to make 1.50 liters of a 0.500 molar NaCl solution? So this time we're going back to grams. We're wanting grams of NaCl to do two steps here. We're going to use the fact that molarity times volume gives me moles of solute. Okay? And then I'm going to use moles of solute times molar mass to give me grams. Now, when I'm doing molarity times volume to give me moles of solute, we need to make sure that our volume is in liters. And when I look up here at the given piece of information, our volume is in liters, and there's our molarity. So those are our two given pieces of information. So my step one is going to be calculating moles of solute, which is going to be 0.500 molar, which remember stands for moles over liters, times the volume, 1.50 liters. Notice liters and liters divide out, I'm going to be left in moles. So 0.5 times 1.5 should give me, 0.750 moles, and in this case it's NaCl because that was our solute. Okay? Now, to go from moles of NaCl to grams of NaCl, I need the molar mass. It's part of my step 2. So 1 mole of NaCl and it's 35.453 plus 22.990. So 1 mole of NaCl has a mass of 58.443 grams. And then we can go 0.750 moles of NaCl, build our conversion factor using molar mass, 58.443 grams of NaCl, 1 mole of NaCl, moles and moles of NaCl divide out, and I get 43.8 grams of NaCl. We can all do that, right? Okay. Let's see. I'm getting better, guys. Okay, now, let's scroll on down here. We all remember that sometimes when we want to make a solution, the concentration we want to make is so small that weighing out the amounts of material is kind of hard. So we work from what's called the stock solution. A stock solution is a solution that has a reasonable concentration to measure out the amounts for. You know, lots of times you'll find stock solutions that are 1 molar. Or 12 molar. When I buy HCl, it comes in a stock solution that's 12 molar. 12 moles of HCl per liter of solution. It can give you a nasty burn if you spill it. Okay? What we do when we have something in a stock solution form and we want to make a solution of lower concentration is we do a dilution problem. Okay? Now, when we're doing a dilution problem, we work on, from the equation, molarity of the initial solution times volume of the initial solution has to equal molarity final times volume final. Now what this means, molarity times volume, remember that gives you moles. And in a dilution, the number of moles of solute don't change You're just changing the volume that they're, the pool they're playing in. They go to playing in a bigger pool. So it decreases the volume. So we're gonna look at a dilution problem. And you guys can look at problem 50, but I wanna show you a problem that we're gonna encounter in lab. Okay? Something that we're gonna do in lab. Let's look at this problem. Over and over again in lab, we're gonna mix solutions together to initiate reactions. The minute that I mix two solutions together, I change the concentration of everybody in the pool. Because when I mix them, I've increased the volume. So everybody's concentration is going to decrease after mixing. So here's a problem. It says, what is the concentration of sodium chloride and potassium nitrate if 15 milliliters of a 0.1 molar NaCl solution are mixed with 20 milliliters of a 0.2 molar potassium nitrate? So I've got 15 milliliters of a 0.10 molar NaCl, and I've got 20.0 milliliters of a 0.20 molar KNO3. Okay, so let's go white screen. All right, so for our NaCl, the molarity initial was 0.10 molar, and we had 15 milliliters of it. We want to know the molarity final, and what's the final volume? Well, I took 15 milliliters and 20 milliliters of the two solutions and mixed them together, so our final volume is 35 milliliters. Now, the nice thing about a dilution problem is I don't have to convert my volumes to liters. As long as the volume units match from the two sides, doesn't matter what the volume unit is. Because notice, milliliters here and milliliters here divide out. So 0.10 times 15 divided by 35 says that molarity final is 0.043 molar. Okay, if we do the same thing for the potassium nitrate, then the molarity initial was 0.20 molar. The volume of the potassium nitrate solution was 20 milliliters. Molarity final, we don't know, and it's the same final volume, 35 milliliters. So 0.2 times 20 divided by 35 says that molarity final is 0.114 molar. Everybody see where everything came from? And we're going to do that a lot in lab. Okay? Every time we initiate a reaction, we're going to be interested in how much of the stuff we had at the moment the reaction, well, what the concentrations are at the moment that we initiated the reaction. So we'll be calculating, we'll be doing this dilution stuff just like this problem a lot. So, want to make sure you're comfortable with it. Everybody okay? Yes. All right. Now, there are other ways to express concentration. Okay, we can talk about mass percent, volume percent, mass volume percent, and mole fraction. Now, mass percent, volume percent, mass volume percent are not really used that much in chemistry. They're used in medicine, Okay, and I think it's just because most medical people hated chemistry when they took it, and they didn't want to do anything that a chemist would do. Now, once upon a time, years and years ago, this was full of fluid. It has slowly evaporated out over time. But if you look here on the IV bag, and no, I'm not giving anybody an IV from this one now. This one's been hanging out in my drawer for about 15 years. It started out as a 0.45% sodium chloride solution. Now, chemists balk a little bit at percentages because notice there are three kinds. And if I look at this labeling, does it tell me what kind of percentage that it is? It doesn't. I have to guess. Was it a mass volume percentage? Since sodium chloride in its pure form as a solid is probably a mass volume percentage, but it can't be 100% sure, and we don't like ambiguity. Okay? So we're not going to worry about calculating percentages because we don't use them in the lab. Alright, now your book may try to, there's some problems in your book. I try to avoid all the problems that have percentages in them in mastering, but about the time that I think I've got mastering figured out, it always slips a ringer in there. Let me know if it does. Okay? We don't use mass percentages very much. Mole fraction, there are a couple of situations where we need to use mole fraction. Mole fraction is just what the name implies. I take moles of compound or substance A in the mixture and divide it by the moles of A plus moles of B plus moles of C for however many things are in the mixture. Okay? So, if I had a mixture that was 1.2 moles NaCl, 6 moles of H2O, and 0.5 moles of KNO3. And my mole fraction of NaCl would be 1.2 moles over 1.2 plus 6.0 plus 0.5 moles. Now notice the moles and moles divide out. It's going to be unitless. So 1.2 plus 6 plus 0.5, 7.7. So 1.2 divided by 7.7. I get a mole fraction here of 0.16. Mole fractions are pretty easy. The only thing that can make them harder is if you were given the amounts of each material in terms of grams, and you'd have to convert it to moles before you calculate the mole fraction. There's one problem here when we're talking about things that affect solubility, where mole fraction is going to pop up. So it's kind of a, for us right now, it's a one-off kind of experience. Questions? Go forward, yes. Yay. Come on. Come on. Okay. Now, the last way to express concentration is going to be one that's going to be very important to us for the last third of this chapter. And that's molality. Okay? Sounds very similar to molarity, but it's molality. The symbol for molality is a lowercase m. Molality is moles of solute divided by kilograms of solvent. Now, the reason that molality is important for us as a way to express concentration is because molality doesn't change with temperature. Your moles of solute doesn't change with temperature. Kilograms of solvent won't change with temperature. Molarity is in terms of moles per unit volume. Volume changes slightly with temperature. So if I make a solution at 20 degrees C and I take it up to 80 degrees C, the volume actually has increases and the molarity has gone down a little bit. Okay? It changed. If I'm doing really delicate work, that change can mess up my results. So if we're doing experiments where we're going to be changing the temperature and concentration is going to be important, we will calculate concentration in terms of molality instead of molarity. So let's look at a molality problem. Okay? So I'm going to invent, because I can. So let's find the molality. Given 15.7 grams of NaCl dissolved in 175.0 grams of water. Okay. Now I know by looking at the way this information is given to me, NaCl dissolved in water, that NaCl is my solute and that water is my solvent. Since I'm calculating molality, I know that I'm going to have moles of solute over kilograms of solvent. So I'm going to need to take the NaCl and convert it from grams to moles, and I'm going to have to take the water and go from grams to kilograms. So 15.7 grams of NaCl, 1 mole of NaCl, and it's 58.44 grams of NaCl. Okay, grams and grams of NaCl divide out. So 15.7 divided by 58.44, I get 0.26865. That's overkill on significant figures. Remember, I don't want to round really until the end of the problem. And then 175.0 grams of water times 1 kilogram for every 1,000 grams. So that's 0.1750 kilograms. And then molality will be 0.2685 moles of NaCl divided by 0.1750 kilograms. How many significant figures should my answer have? 3. Very good. So I get 1.54, and you can use the little m, or you could have written moles of NaCl over kilograms of water. Some people just write moles over kilograms, but it's better to put all the details in, or just use the little symbol. How does that look? It's not too bad, right? Any questions? All right, now, bringing up the term solubility again. Solubility expressed by, solubility is a way to express the concentration of a solute at the saturation point. when the solution is holding the maximum amount of solute. Solubility then is a concentration. Common ways you see it expressed are in terms of grams per milliliter, very common in geology. We'll also see it in terms of molarity, okay? Sometimes you'll see it as molality, but usually grams per milliliter or molarity are the two common ways that solubility is expressed. 3 or 4 chapters down the road, we're going to talk about things that can affect, well, we're going to talk about slightly soluble salts, the SSSs, and we'll be talking a lot about solubility. Okay? Now, there are several factors that can affect solubility. The most important, of course, is the nature of the particles themselves. We've already been talking about, whether the molecules are polar or nonpolar, whether they can generate a, dipole-dipole interaction or hydrogen bonding, anything like that. That has the biggest role to play in the mixing of a solute and a solvent, the nature of the components. We can't control that, okay? But there are some factors that we can control. And the first thing that we can manipulate to manipulate the solubility of a solute in a given solvent is temperature. So let's talk about temperature. If I'm dissolving a solid or a liquid up in a liquid solvent, the effective temperature on solubility depends on the enthalpy of the solution formation. Okay? So if I'm dissolving a solid up in a liquid or a liquid up in a liquid, its solubility depends on delta H. If the value of delta H is negative, if the overall mixing process is exothermic, increasing the temperature actually decreases the solubility. Okay? And that means that decreasing the temperature would increase the solubility. It's counterintuitive. We always think, we'll increase the temperature, they're going to mix better. But there's certain situations that increasing the temperature actually decreases their ability to mix. Okay? So if the process of mixing is overall exothermic, increasing the temperature decreases solubility. When we talk about equilibrium, I'll bring this back up again and I'll be able to explain to you why. Okay? If the overall process of mixing is endothermic, requires an input of energy, increasing temperature increases solubility, and decreasing temperature decreases solubility. So, if we look at this graph here, move this up just a little bit. Here are several salts, and their solubilities is a function of temperature. One of these things is not like the other. Which salt stands out as being way different than the other ones? Cesium sulfate. Okay? Because notice, as temperature increases, its solubility decreases. But with everything else, as temperature increased, solubility increased. Sodium chloride was almost flat, but still, as temperature increased, it went up slightly. That tells me that potassium chlorate, sodium chloride, potassium nitrate, sodium nitrate, their dissolving process in water is endothermic. Cesium sulfate dissolving process is exothermic. Okay? So this is one of those effects that we can see. All right? Okay. Now, things dissolving up in the liquid, I avoided talking about gases, and that's because we treat gases kind of separately. Let's think about the process of a gas dissolving up in water. The process of a gas dissolving up in water is always exothermic, okay? And it is a process in which entropy decreases. You think about a gas particle in the gas phase. It's running wild, whee! And it goes a long way before it runs into a wall, and it runs into somebody else, and it's free, okay? It's not interacting. There's lots of space and lots of movement. When it dissolves up into a liquid, it's going 2 steps, oh, sorry, 2 steps, ah, sorry, 2 steps, ah, sorry, 3 steps, I'm free, sorry. Keeps bumping into things. So when a gas dissolves up in liquid, there's a tremendous decrease in entropy, okay? Also, it's exothermic because it wasn't interacting with anybody, and when it dissolves up, it has formed those attachments, and when those attachments form, energy is released. Both of those things stack against gases dissolving up in warm water. So for a gas, as temperature increases, the solubility always decreases. And when temperature decreases, solubility always increases. Okay? Think about opening a warm can of soda as opposed to a cold can of soda and how much they fizz. Okay? Also here in Alabama, people like to stock ponds with trout in the winter months, but you better fish them out before, let's say, May, because if you don't, then all your trout are going to go belly up in your pond, because trout are very sensitive to oxygen content in the water. And as the water warms up, the oxygen content go down, and your trout actually suffocate. They can't breathe, and they all go belly up. And then when they go belly up on their own, they're not good to eat. You gotta catch them. So, for gases, always, as you increase the temperature, you decrease solubility. You decrease temperature, you increase solubility. So if you are a fish and you want high oxygen content and you are a ocean-going saltwater fish, where do you want to live? You want to live at the equator? Do you want to live at the poles? You want to live at the poles. The water is colder and it has a higher oxygen content. There's actually a lot of life at the poles because there's high oxygen content. You have a lot of krill, you have a lot of plankton that feeds fishies that like to eat, and then whales go and eat the fishies. Okay? But we have lots and lots of oxygen content, higher oxygen content at the poles. Okay. The other thing that can affect the solubility of a gas in a liquid, okay, just for gases, is pressure. Under pressure. Okay? Turns out, as pressure goes up, solubility goes up, and as pressure goes down, solubility goes down. Now, let me kind of scroll this up. Okay? If I have a gas in equilibrium with its dissolved phase, so I have carbon dioxide molecules here above water, and some of the carbon dioxide is dissolved in water. When it's in equilibrium, the number of particles jumping into the gas phase equals the number of particles coming out going into the liquid phase. If I push on it, start squeezing this sucker down, I concentrate the gas particles up here. They hit the surface of the liquid now more often. Okay, if you think about these gas particles running around and they have all of this space to run around in, okay, think about the number of times it hits the wall in a second, and then I were to go from just here to here. I'm doing weird football drills, no. I would clobber into the wall more often, okay? So when that happens, you end up having more collisions with the surface, and more often than not, they stick and get dissolved up. So the more collisions they make with the surface, the more likely they are to go into the liquid. So by increasing the pressure, you increase the solubility. You essentially are forcing more gas into the liquid. If we were then to pull it up, okay, so kind of reverse it, go this way, so that I pulled it back up again, particles, carbon dioxide particles that are at the surface, if they get bumped from the bottom and given some energy, they'll pop out. And they've got more room to run around in here. They're going to encounter the surface of the liquid less often. So we're going to get a lot of them jumping before more come back. So I increase the pressure, I increase the solubility, I decrease the pressure, I decrease the solubility. And we have all experienced this when we open a can of soda. Okay? When we have a can of soda here, there's dissolved gas in there, and there's a very little volume at the top of the container that is full of just carbon dioxide gas. When we pop the top, number one, we reduce the total pressure over the surface of the liquid, and number two, we reduce the partial pressure of carbon dioxide over the surface of the liquid. And the liquid in here then forms bubbles and fizzes. I like my fizzy soda, but it's due to the carbon dioxide coming out of solution. When they make carbonated beverages, the partial pressure of carbon dioxide over the surface of the liquid is around 4 atmospheres. And they do it at around 4 degrees C. So they do it at a low temperature and a high pressure to get maximum fizzy. One of the fizziest sodas out there is 7-Up. It's got a real high carbonation level to it. It fizzes more than, let's say, Coca-Cola does. Just for your personal. Now, we can relate the pressure of the gas above the surface of the liquid to the solubility of the gas using Henry's law. Okay? Henry's law says the solubility is equal to solubility constant K times the pressure of the gas. Now, there's different solubility constants for different gases. Let me kind of scroll this up here a bit. But it's pretty straightforward. So let's say that I had oxygen. So I had O2, and its partial pressure of O2 was 1.2 atmospheres, and that's pretty hot. Okay? And I wanted to know the solubility. Well, the solubility would just be the K value, 1.3 times 10 to the minus 3, molarity over atmospheres, times 1.2 atmospheres, so 1.3 exp 3 negative times 1.2 gives me 1.6 times 10 to the minus 3 molar. So that would be the solubility for oxygen and water at 25 degrees under that partial pressure of oxygen, which, by the way, is high. Now, one of the things I want you to notice here, notice how much higher the K value is for ammonia, let's say, as compared to helium. Why do you think ammonia has a much higher K value than does helium? Go for it.
Is it polar?
Yes, very good. It is polar and it can hydrogen bond with water. So from the get-go, it wants to dissolve up in water more than helium does, which is a very small single atom that has to be polarized to interact with water. Okay, so ammonia with water can dipole-dipole and hydrogen bond in dispersion. All that helium can do is a dipole, induced dipole in dispersion. It's not a good trade-off. So that's why it has a much smaller K. Everybody feel comfortable with that? I figure those are pretty bunny hop problems, right? You want like 4 or 5 of those on the test. All right. Now, pressure doesn't really play a role when we're dissolving solids in liquids or liquids in liquids. Pressure really only plays a role when a gas is being dissolved in a liquid, because when we look at solids and liquids, they're non-compressible. So squeezing in on them isn't going to change the volume, or it's not going to change the volume enough for it to make any difference in the mixing process. How am I doing on time? Oh, we're doing well. Everybody okay so far? All right. Now, everything in this chapter has been leading up to colligative properties. Okay? And our experiment on Thursday is going to be on colligative properties. I'm thinking about modifying the experiment a little bit. I've been tinkering with this experiment over the last couple of years, and it's getting better, but I want to make it even better still. I want to check out a piece of equipment and see if it'll run out a few more decimal places when taking temperature. And if I can get that to happen, we're going to have a fun experiment on Thursday. So stay tuned on Wednesday. I'll give you an update on whether or not I've modified the lab and whether I'm going to give it to you as a handout or if it's going to be on the computer that you can print it out. So, watch out for that on Wednesday. So let's talk about colligative properties. These are some properties of the solution that depend only on the number of solute particles, okay? The concentration of solute particles and not identity. Okay, so taste wouldn't be a colligative property, because the taste of a mixture of water and sugar would be different than the taste of sodium chloride and sugar, the sodium chloride and water. So colligative properties depend only on the number of solute particles, the concentration of solute particles, and not the identity of the particles. Our colligative properties that we're going to be interested in are vapor pressure, boiling point, freezing point, and osmotic pressure. Okay? Now, there are lots of different solvents that you can experience. Okay? Water is the most common. Methyl alcohol, benzene, acetone, there's a huge list. We're going to concentrate in on water solutions, okay? And we're only going to worry about water as our solvent as we look at colligative properties. That's going to make our life a little easier. We're also going to stick to non-volatile solutes. Volatile doesn't mean gets grumpy quickly here. Volatile in terms of chemistry and what we're talking about means the ability to jump from solution into the gas phase. A non-volatile solute, if you warm up the solution, cannot jump into the gas phase. Oxygen is not a non-volatile solute. Oxygen, remember, as we increase temperature, is going to come out of solution and jump into the gas phase. So when we're talking about colligative properties, we're not going to be talking about gases being dissolved in a liquid or in water. We're going to be looking at solids being dissolved in water and liquids that are dissolved in water that don't jump into the gas phase as we heat the solution. So ethyl alcohol is not going to be part of our discussion here when we look at colligative properties. Because ethyl alcohol, as you heat it, okay, with water, it actually comes out of solution and goes into gas phase and leaves the water behind, if you control the temperature just right, that's how you distill alcohol. Okay? So really, we're going to be concentrating in mainly on solid initial solutes that end up being dissolved in water. So we're limiting our scope. Okay? Now, when we look at these non-volatile solutes, they're either going to be considered an electrolyte or a non-electrolyte. Where do you hear the term electrolyte in everyday usage?
Sports drink.
Yes, sports drinks. Okay? Now, let's figure out what they're selling us when they tell us that they are replacing our electrolytes. An electrolyte, when dissolved in water, dissociates into ions or ionizes to produce ions. So, electrolytes, when dissolved in water, create a solution that conducts electricity. So, sodium chloride is an electrolyte. Potassium nitrate is an electrolyte. Hydrochloric acid is an electrolyte. Okay? Ammonium chloride is an electrolyte. Anything that dissolves in water and either separates out into its ions or reacts with water to produce ions is an electrolyte. So that means salts are electrolytes and acids are electrolytes. Soluble salts, strong acids, strong bases, 100% ionize in water. Okay? And they're called strong electrolytes. So if I were to put, well, we'll talk about, I'll do it in just a second. Acids that only partially ionize in water are called weak electrolytes. Okay? So acetic acid, we'll talk about that later on, is a weak electrolyte. It doesn't 100% produce ions in water. So, let me kind of scroll up here a second. So if I had a 1.0 molar NaCl solution, my concentration of particles would be 2.0 molar. Because for every one sodium chloride formula unit, there's one sodium ion and one chloride ion. And sodium chloride is a strong electrolyte. Okay, if we had a 1.0 molar magnesium nitrate solution, our concentration of particles would be what? Magnesium nitrate is an ionic compound. It contains one magnesium ion and two nitrate ions. So that's a grand total of 3 ions. So it would be a 3.0 molar concentration of particles. Starting to kind of get the feel for it? Want to try one more? So let's say that I have a 1.0 molar aluminum nitrate solution. Another 3. What's my particle concentration?
4.
Yes. You guys got it. Okay, not bad, right? So anytime you look at a salt and you are asked about particles in solution, you know that you need to look at the salt and figure out how many cations, how many anions, add them together, so that you can calculate your number, your concentration of particles. Okay, now, the book kind of plays some games with you here. You might see a question like this. What is the concentration of nitrate ions in a 1.00 molar, let's see, no, where is that? Magnesium nitrate solution. Well, in 1 formula unit of magnesium nitrate, how many nitrates are there? 2. So our concentration of nitrate here would just be 2 times 1, 2.00 molar. Okay? So watch out for things like that. Don't be spooked. You got this. So, for salt, the concentration of salt, the concentration of particles in the solution is going to be different. If we have a covalent compound, like glucose, or ethanol, or fructose, okay? They stay whole in water. They dissolve up through a different dissolving process. So, if I had a cancel, I screwed up, I apologize. So if I had a 1.0 molar glucose solution, C6H12O6, what's my particle concentration? What kind of molecule is glucose? Ionic or covalent? What kind of compound? It's covalent. I know it's covalent because it's got all nonmetals. Carbon, hydrogen, oxygen, all nonmetals. Since it is a covalent compound, when it dissolves up in water, it stays intact. So my concentration of particles would be 1 molar. Okay? Now, the covalent compounds you gotta watch out for are something like an acid. So 1.0 molar HCl. Okay? Hydrogen, remember, is written, you notice is written first in the formula. That's that blinking red light that screams I'm an acid, pay attention. Acids ionize in water. The particle concentration here is 2.0 molar. Now, I'm not going to hit that very hard this chapter. We're going to spend 2 whole chapters talking about the behavior of acids in water, and that's where we'll get down to the nitty-gritty of acids. But I want you to be aware that even though this is a covalent compound, it ionizes in water. Now, in a perfect world, and when a salt dissolves up in water, all of the ions should separate from each other. Do we live in a perfect world? No. We don't live in an ideal world. In the real world, sometimes some of the ions stick together and form clumps. Okay? We don't get 100% separation. Because of that, be doing is we're gonna try to determine the Van Hoff's factor for a salt. Okay? The Van Hoff's factor, given the symbol lowercase I, tells us something about how much clumping we get when the salt dissolves up in water. We always assume that for a strong electrolyte, we get 100% separation of the ions. So that I equals the number of ions contained in the formula unit. Okay? But in the real world, sometimes they're less. Okay, for a non-electrolyte, I is 1. Our measured I is 1. Have I gone over my time? No, I haven't. I've still got 9 minutes. Okay. For sodium chloride, okay, we'd expect it to be 2, because there's a sodium ion and a chloride ion. It's 1.9. Okay, it's a little bit less. If we look at magnesium chloride, we'd expect 3, it's actually 2.7. And notice for iron 3 chloride, we'd expect 4 and we get 3.4. They clump together a lot. Okay? So Van Hoff's factors. We're going to experimentally determine a Van Hoff's factor. I'm not quite sure which salt I'm going to use. I'm going to look at solubilities so that we can get some good numbers. Okay? But we're going to do that. All right. Now, we've already done a couple of those, so I think we're okay there. So we've kind of set the stage to talk about our colligative properties. In general, we can say that the larger the solute particle concentration, the greater the shift in things are going to be. The greater the shift in vapor pressure, the greater the shift in freezing point, the greater the shift in boiling point from that of the pure solvent. Okay? So I think that this is probably a perfect place to stop, because once we start running through our colligative properties, I'll kind of want to do it all in one fell swoop. Okay, so anybody got any questions? All right, how is that? You should now be able to complete that first problem sheet, because we've now talked about molarity, and so you should be able to do those problems. If you have any problems, let me know Thursday, and Thursday I can take a little time and we can look at anything that we need to look at. Okay? Is there anything else? Okay, you guys are free and clear. Thank you for being good students today.